Welcome to this lesson on electric potential and voltage. In this video, we'll explore one of the most fundamental concepts in electricity, understanding electric potential energy per unit charge. By the end, you'll have a clear grasp of what voltage really means and how it relates to the energy that charges carry in an electric field. Let's start by defining electric potential. Electric potential at a point is the amount of work done per unit positive charge to bring it from infinity to that point in an electric field. Think of it this way. When you move a charge through an electric field, you're doing work against the field's force. The electric potential tells us how much work is needed for each unit of charge. This concept is crucial because it helps us understand the energy landscape created by electric fields. It's important to distinguish between two related but different concepts. Electric potential energy is the total energy that a charge possesses when it's placed in an electric field. On the other hand, electric potential is the energy per unit charge at a specific point. In simpler terms, electric potential energy depends on how much charge you have, while electric potential is independent of the charge amount. It only depends on the location in the field. Now let's talk about voltage, which you've probably heard of before. Voltage is the difference in electric potential between 2 points in an electric field. This is why voltage is also called potential difference. When we say a battery has 9 volts, we mean there's a 9-volt potential difference between its positive and negative terminals. This potential difference is what drives charges to move through a circuit. The relationship between electric potential energy, and charge is given by a simple but powerful formula. V equals PE divided by Q here. V represents the electric potential or voltage, PE is the electric potential energy, and Q is the charge. This formula tells us that to find the electric potential at a point, we divide the potential energy by the amount of charge. It's the foundation for understanding how energy is distributed in electric fields. Let's look at the units we use to measure these quantities. Electric potential is measured in volts, represented by the capital letter V. Electric potential energy is measured in joules, represented by the capital letter J, and charge is measured in coulombs, represented by the capital letter C. Understanding these units helps us see that 1 volt is equal to 1 joule per coulomb. In other words, if 1 coulomb of charge gains 1 joule of energy, it has moved through a potential difference of 1 volt. To make voltage more intuitive, let's use a helpful analogy. Think of water pressure in a pipe system. Water pressure is the push that moves water through pipes from high-pressure areas to low-pressure areas. Similarly, voltage is the push that moves electrons through circuits. Just as higher water pressure causes water to flow faster, higher voltage causes more electric current to flow. This analogy helps us visualize why voltage is often called electrical pressure. Voltage has several important properties worth remembering. First, it is a scalar quantity, meaning it has magnitude but no direction. Second, voltage can be positive or negative, depending on which point we consider as our reference. Third, voltage is always measured between 2 points, never at a single point in isolation. And fourth, voltage is independent of the path taken between those 2 points. This last property is particularly important because it means we can calculate voltage differences without worrying about the specific route charges take. Electric potential and electric field are closely related. The relationship is expressed mathematically as E equals negative dV divided by dr. This equation tells us that the electric field is the negative gradient of electric potential. In simpler terms, the electric field points in the direction where the potential decreases most rapidly. The stronger the rate of potential decrease, the stronger the electric field. This relationship helps us understand how charges experience forces in regions where potential varies. Let's review the key points from this lesson. First, voltage is energy per unit charge, representing the work done to move a charge between 2 points. Second, it's measured in volts, abbreviated as V. Third, the fundamental formula relating voltage, potential energy, and charge is V equals PE divided by Q. And finally, voltage acts like water pressure in pipes, providing the push that drives electric current through circuits. Understanding these concepts gives you a solid foundation for exploring more advanced topics in electricity and electronics.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.